Let me first talk about your past quiz question. I guess one of the questions is not understood well enough. So, quiz question. I guess it was this one form, right? X dy minus y dx divided by x squared plus y squared. You were asked, so this is a one form on where R2 minus 0, 0, right? It is
Hocam
defined
pardon,
everywhere.
tahta
Evet.
sağ tarafta kaldı da.
Tamam. Okay. Oops. Okay. Okay. So this is a one form on R2 minus 0, and you were asked to find, if possible, so you were asked to show that this is closed but not exact. So you may check that this is closed, so that W is closed. Whether it is exact, is it exact? In other words, is there a zero form? Zero form. Well, zero form means a function. In other words, a function, let's say phi or f, let me say f from where? R2 minus 0 into R, so that omega is df. Okay, is there a function like this, a potential for this one form? I guess most of you did the computation and found one candidate f, right? F from the you may also do it from your what, ordinary differential equations knowledge. So such f exists, but such f exists, and it is up to a constant. So you just integrate this one form, and f turns out to be tangent inverse, I guess y over x over y. Değil mi? Bunun differential'ını alırsanız şunu elde ediyorsunuz. What is df? Df is x derivative of this dx plus f derivative of y dy. X derivative of this is what? It is 1 over y minus tangent inverse. Yes. So it is the derivative of inside. Derivative of inside is just 1 over y, and then 1 plus this gadget dx plus derivative of inside, which is minus x over y squared, and then 1 plus x over y squared dy. What is this? This is just x squared plus y squared, and y squared comes up. So you get y dx, and here you will have x dy. So it is exactly this differential form. But you know, you should be careful. This function is not defined on R2 minus 0, right? This is undefined if y is 0. So this is defined only on R2 minus y axis. okay, y-axis. You have to subtract the y-axis. Therefore, this one form is not exact, okay? There is a function which looks like it's a differential, it's a potential for this, but it is only defined R2 minus 0. And this is a very good geometric reason, I mean, why this is the case. You know, this omega is what? Omega is, if you, you know, this theta is f, you may consider this as theta. Which theta? If you have a point here, let's say x comma y, and this angle is so x over y, x over y. So if you say theta is this, then tangent theta is what? Tangent theta is x over y, right? So theta is tangent inverse x over y. So your f is just theta. Okay. And if you take the differential of this, you really get omega. This is omega. No problem with that. So your omega is just df or d theta. But this theta function measures this angle, right? It measures this angle. If you are at a point here, it measures this angle. This function is not continuous on R2 minus 0. Why is that? Now, suppose you are at this point, okay? You are at this point. Then this angle is 0, right? So theta is 0 here. And then you start moving. Theta becomes pi over 2. And then you continue moving. Theta becomes pi. And then 3 pi over 2. And then when you come back to this point back, theta has to be 2 pi. 2 pi. But you said it was 0, okay? So this theta is not a well-defined function on R2 minus 0, okay? It is multi-valued. Therefore, so theta is not a well-defined function on R2 minus 0, 0. It is, theta is a multi-valued function on R2 minus 0, 0. Okay? Multi-valued because it takes many values. It takes 0 and then pi, 2 pi and so on. That's why this one form, so this is not the differential of a function defined on R2 minus 0. Therefore, this omega is not is not exact. Since omega is not the differential of a function defined on R2 minus 0, omega is not exact. Okay. Actually, it is, you know, the only non-exact closed one form, basically, on R2 minus 0. And what it does, this one form, it measures, if you give me a closed curve, okay, let's say C, and if you integrate omega over the C, what it will do, it will start from this point and start measuring the angle. When you make, you know, one revolution, let's say you will come here, it will, the value will be 2 pi. and then another 2 pi, and then another 2 pi. So this is just 2 pi times the number of turns. Let's say n is the number of counterclockwise turns of C around the origin. Okay, it measures how many times it turns around the origin, and this is the only actually meaningful one form, closed one form on R2 minus 0, because the only meaningful thing you can do on R2 minus 0, right? This is whole plane, there is nothing on it, just one hole. What can you do? The only meaningful you can do, just integrate curves so that you measure how many times it goes around the origin. Okay, that's why it is the only form. Okay. Anlaştık mı? That's not something I will ask in the exam, but these forms have a lot more meaning, both geometric and topologic. This is one nice non-trivial example. Yeah, but then the number will change. So suppose your curve is like this. If you shift this like this, it will go around the origin once. Oh, omega. Yeah, of course. Yeah, you may measure the how many times a curve goes around another point, not 0, 0, but another point. Yes, you can do this. So you just shift x and y a little bit, okay? X minus x0 dy minus y0 dx, and then x minus x0 squared plus y minus y0 squared. This will measure how many times a curve will go through, will go around this point. Okay. All right. So let's come back to our study. We were, I guess, discussing orientation and what? Orientation and functions. So what was an oriented last time? So let me okay, I'll go over what we have done. A frame, let's say E1, E2, E3 is positively oriented, right? Positively oriented. If and only if arkadaşlar birinizin mikrofonu açık ama. If and only if what? What was the definition? E1 cross E2 dot product with E3 is positive, right? This is, of course, the same thing as this determinant. You write your E1, E2, E3 as rows of a matrix, and you take the determinant. Determinant is just E1 cross E2 dot product with E3. Okay, and then I guess we talked about isometries, and isometry is a function which preserves distance, and we wonder whether an isometry preserves orientation or not, and how can we check that. But first, let me tell you, if we have a function, how it maps a frame to a frame at the image point. So if you have a point, let's say P here, and a vector VP, and suppose you have a function, this point is mapped to, let's say, Q, f of P, and then this vector will map to a vector. I guess we denoted it like F star VP or something, right? And what is this gadget? Well, if F has, let's say, 3 components, F1, F2, F3, where each one is a function of, let's say, X, Y, Z, then what is FVP? F star VP is just these functions. So F1 star, F2 star, and F3 star VP. And what are these? A function applied to a vector is actually the same thing as the vector applied to the function, right? This is just VP of F1, VP of F2, and VP of F3. And what is this? That is just, so F star VP is just, right? This this gadget is just the directional derivative of F along the vector V at the point V. So it is just the directional derivative of F1 at the point V along the vector V. And then directional derivative of F2 at P along the vector V, and directional derivative of F3 at P along the vector V. Bunu böyle yazmıyoruz, right? We don't write it this way. We write it this way, right? Directional derivative is just the dot product. Okay. Let me write it this way. But what is this? If in matrix form, this is nothing but the following. You just write here F1, P, F2P, and F3P. And you just multiply this by the vector V, right? V is a vector. This is a matrix, 3 by 3 matrix, and it is nothing but this expression. So F star actually, F star VP, is a vector at the point Q, and the vector component is nothing but the Jacobian of F applied to the vector V, okay? So a function maps points to points, and the vectors at this point are mapped to vectors at this point by the derivative of F, okay? So this is just F star VP, and this is nothing but you just take the Jacobian of F and apply it to the vector V, okay? This is a 3 by 3 matrix. This is a vector. You just multiply it. So this row is multiplied with the vector V. That is this dot product. And then this row is multiplied with it is this dot product. And then this vector is multiplied with this. It is this dot product. Maybe I should be more careful. You know, this way I get a column vector, but this is a row vector. So maybe I should say transpose or something like this. Okay, but doesn't matter. Really. Tamam mı? Yani neymiş? Fonksiyonlar noktaları taşıyor. Türevleri de, Jacobian'ları da o noktalardaki vektörleri taşıyor. Alright. Alright, let's move. Let's see some examples of differentials like this. What about, for example, translations? Translation'ları nasıl göstermiştik? Hatırlıyor musunuz? Özel bir harf kullanmış mıydık? Did we use a special letter for translations? Efendim? T. Evet. Değil mi? Okay. So T is a translation. Let's say translation along the vector. Say U. Okay. So what is T of okay. When you give me a point, it will just add to this point the vector V. Okay. Bir P vektörü alıyorsunuz. Buna ne yapıyorsunuz? V vektörünü ekliyorsunuz. P plus V'ye gidiyorsunuz. Bakalım bunun differential nedir? What is the derivative of this? Sorry? T plus U. Yes. I'm sorry. What is the differential of this? Okay. Well, so I have to write down its Jacobian, but let me write first in coordinates what this is. Say P is the point X comma Y, Z, and U is the vector U1, U2, U3. So what is T, X, Y, Z then? Well, this is just X plus U1, Y plus U2, and Z plus U3. So what is F star? F star VP. If you give me a vector VP, it is given by what? You have to take the Jacobian of this. Jacobian of this. So I'll just take derivative of these functions with respect to X, Y, Z, right? So this is X plus U1. What is the derivative of this with respect to X? It is just 1. What is the derivative of this with respect to Y? 0. With respect to Z? 0. So I am just forming actually gradients. So this is F1, this is F2, this is F3, okay? So and then gradient of this 0, 1, 0, and then 0, 0, 1. And then here you write V1, V2, V3, okay? And what you get, of course, just VP itself. So the differential of a translation is basically the identity function. It doesn't do anything to the vectors, right? It is identity. Okay. Yes, yes, you are right. This is VP plus U. You are right. I have a vector here, VP, and then I get this vector, VP plus U. The vector component is the same. The point it stands is different, okay? It's at the point P plus Q, P plus U, but the vector component is the same. What about an orthogonal transformation okay, let's take,
Hocam
evet,
bir de yukarıda F star dedik ama o T star falan mı hani ya da
you're right, this should be T star, yes. Okay. Suppose C is a linear map given by C of, let's say, P is just A times P for some 3 by 3 matrix A. So it is just matrix multiplication. Here I regard P as a point in R3 or as a vector so that I can multiply with the matrix. So what about the differential of this? What about the differential of this? Well, in so CP is just the matrix A, let's say Aij, and then here I have the point P, X, let's say, I will write, of course, it this way, X, Y, Z. Yeah, da şöyle yazayım. Maybe, okay. So A11, A12, A13, A21, A22, A23, A31, A32, A33, and okay, let's say the coordinates of P are X, Y, Z. So its image will be just, this matrix multiplication. Well, what is the differential of this? What is C star? P at V. Well, I have to take the differential of this, okay? So maybe we should write it this way. In, as a vector, this is just the first row, right? So the first row, let me say R1 dot product with this is the point P, dot product with P. R2, the second row. So this is R1, R2, and R3. R2 dot product and R3 dot product V, P. So what is the, so this is my, let's say F1, F2, and F3. What is the C star then? Well, I have to take gradients of these functions. What is F1? F1 is just, right, let me write it this way. F1 is just F1 X, Y, Z is just what? A11 times X, A12 times Y, A13 times Z. What is the gradient of this? Well, it is just X derivative, Y derivative, Z derivative. And then you do the same thing for this one, A21, A22, A23. And then for the third one, A31, A32, A33. So the gradient, I am sorry, the Jacobian is nothing but A. And of course, this is nothing surprising, right? This is just multiplication by a constant matrix. So the derivative is just this matrix again, right? It's like, what is the derivative of the function 2x? you may consider this as a matrix multiplication, 1 by 1 matrices. What is the derivative of this? Just matrix 2, right? 1 by 1 matrix. So the same idea. V, okay. I have to put, of course, V1, V2, V3 here. Okay. So A times V. At which point? At the point, of course, Q, where Q is C of P. So if your map is a matrix multiplication, it is just multiplying its derivative is itself, okay? Peki. Okay. Orientation'a gelince recall that, oops, I forgot, change the board. Okay. Okay. Recall that an isometry of R3 has the form. Neydi? Önce translation sonra rotation mıydı? Okay, so it's like this, right? Okay. So what is the differential then? F star VP. Well, so this is T. You need to take the Jacobian of this, right? And then compute this, evaluate this on the vector VP. Well, composition of two functions. What is the Jacobian? It is just a chain rule. This is just the Jacobian of T, composition Jacobian of C, VP. But Jacobian of T, translation, right? Jacobian of T is just the identity matrix, right? It's here, right? This is the Jacobian of translations. It is just, so this is GT, it is just identity. Let me show it, right? Jacobian of translation is just identity. So this is just identity. So this is just GC VP. In other words, this is just C star VP. No, this is this one. No, it is applied to this vector. But finally, this will be a vector at some other point. But you know, the vector component is just this. And so this isometry şey tarif etmiş miydim? Isometrinin orientation'ı korumasını. Did we define what it means an isometry preserves the orientation? Okay, okay. Yeah, let me just rephrase that. So let me write as a definition. Okay, an isometry is orientation preserving if it maps oriented, positively oriented frames to positively oriented frames.
Hocam aslında geçen haftanın sonunda bununla ilgili bir teorem yazmıştınız
Yeah,
ama
but
onun ispatı
I
kalmıştı
think
sanırım.
I'll do that, but last time I didn't properly define what it means an orientation preserving
O da
isometry.
teoremde hocam parantez içinde yazmıştınız hani.
Anladım. Okay. I'll come to that. Okay, so an isometry is orientation preserving if it maps positively oriented frames to positively oriented frames. In other words, suppose we have a frame here, E1, E2, E2, and E3, and it is mapped under F. F is point is mapped here, and let's say this is F star E1, and then F star E2, F star E2, and then let's say F star E3. Okay, so pek olmadı ama E1, E2. Belki şunu şöyle mi çizmek lazım? F star E3. Yes. Okay. So it maps positively oriented frames to positively oriented frames. If it is the case, then we say that F is orientation preserving. And so for a linear map or isometry, if A is a 3x3 matrix with determinant not zero, then for any frame E1, E2, E3, its image under F under A is AE1, AE2, AE3. Yani şurada herhangi bir noktada bir frame'iniz varsa E1, E2, E3 diyelim. Şöyle. A ile çarparsanız o vektörleri, if you multiply the vectors by A, you get three vectors, AA1, AA2, AA3. AE3. Since the determinant is non-zero, this is an invertible matrix, so you may go backwards also. So if these are linearly independent, so are these. And whether this is orientation preserving or reversing depends what? Depends on whether this is positively oriented or not, given that this is positively oriented. So assume E1, E2, E3 is positively oriented. This means what? E1 cross E2 dot product with E3 is positive one, plus one, right? And suppose A is an isometry. A is orthogonal. A is an orthonormal matrix. So that this is also a frame. So that AE1, AE2, AE3 is also a frame. Then, so we wonder whether A is orientation preserving or not. How can we check that? Okay. Okay. So we have to look at this. But remember, what is this? This is nothing but the determinant of the following matrix: AE1, AE2, AE3. And this is nothing but this, this matrix. So is just the determinant of A times E1, E2, E3. E1, E2, E3. Right? When you multiply with A, you get A times E1. Belki bunu şöyle mi yazmak lazım? E1, E2, E3. A times E1 is the first one, A times E2 is the second one, and so on. And this determinant is just determinant of A times determinant of E1, E2, E3. And this is just one, since it is positively oriented. So this is just determinant A. So this is positively oriented then. This is positively oriented. A1, AE1, AE2, AE3 is positively oriented if and only if this determinant is plus one. Okay. In other words, an orthogonal transformation is orientation preserving if its determinant is positive. Okay. Hence, an orthogonal transformation is orientation preserving if and only if its determinant is plus one. Since it is orthogonal, its determinant is either plus one or minus one. If it is plus one, then it preserves the orientation. Okay. it maps a frame, positively oriented frame, to another positively oriented frame. Okay. Now I think we may pass to so-called fundamental theorem of curves. This was section what? 3.5. This theorem will tell us the following. If you have two space curves, so that they are both unit speed, okay? And if they have the same curvature and torsion function, then you can find an isometry, orientation preserving isometry, which maps one of the curves onto the other one. In other words, you can just rotate this first curve and then translate so that it will just map onto the second curve. Okay, the only difference between them is that one of them is transformed by a what isotopy, orientation preserving isotopy, provided that their torsion and curvature functions are the same. So any curve is uniquely determined by its torsion and curvature functions up to an orientation preserving isotopy. Okay. All right. Let me stop here. I have only 2 minutes. After the break, I'll start this theorem.